Okay. All right. So, have a book? Do you have a book? Go to the library and go get one. We should still do that. You have the notes on there? Go to the library and go get one.
Okay.
Go through the bathroom and then go to that glass door that's right there. Okay. Let's see. All right, so exponential functions. So they've already given us the f of x equals 2 to the x. That's basically the parent function for exponential growth. We are going to be also graphing g of x equals 1/2 to the x, which is basically your parent function for exponential decay. But just kind of looking, remember negative exponents want to be fractions, so 2 to the negative 1/3 is 1/8. 2 to the negative 1/2 is 1/4. 2 to the negative 1 is 1/2. Anything to the 0 power is 1. Of course, 2 to first, 2 second. Right? So they've plotted all those points for us already. Okay. What you want to notice here is that, actually, I'll talk about that in a minute. So remember that negative exponent with a fraction is going to want to flip that fraction. So this becomes 2 over 1 to the positive 3, which would then be 2 cubed over 8 cubed, which would be 8. Right, so that's when you plug in negative 3, why it flips and becomes positive 8. Okay? So then 1/2 to the negative 2 is going to flip that fraction, so it's going to become 2 over 1 to the positive 2, which would then be 2 squared over 1 squared, or 4. So negative 2 would give us 4. So I'm just going to write out a bunch of these here just to save myself. That's a 2. One-half to the negative 1 would just flip the fraction, then raise it to the first power. So 2 to the first power, of course, would just be 2. Anything to the 0 power is 1. Of course, 1/2 to the first power is 1/2. 1/2 times 1/2 is 1/4. And then 1/2 times 1/2 times 1/2 is 1/8. So you should see how these are just kind of opposites of each other. What I want to point out earlier is that I want you guys to notice that this is the way the y values change has a consistent ratio. Okay, that 1/8 times 2 is 1/4. 1/4 times 2 is 1/2. 1/2 times 2 is 1. 1 times 2 is 2. Right? 2 times 2 is 4. 4 times 2 is 8. So there's a consistent ratio here of those y values. In the same way, we have a consistent ratio on these y values. 8 times 1/2 is 4. 4 times 1/2 is 2. 2 times 1/2 is 1. 1 times 1/2 is 1/2. 1/2 times 1/2 is 1/4. 1/4 times 1/2 is 1/8. So there's a consistent ratio here. Right? So that's not a linear idea. Linear ideas are consistent change. So if we add 3 each time, that's consistent change. Or if we subtract 2 each time, that's consistent change. So the change is changing, right? This goes up by 1, then it goes up by 2, then it goes up by 4. The change is changing, but it's changing by a consistent ratio. Okay? This goes down by 1, then it goes down by 1/2, then it goes down by 1/4, then it goes down by 1/8. Okay? So the change is changing, but it's changing in a consistent ratio. So that's what makes it exponential. Okay? Versus being something like linear. So if I plot those points, -3, 8, -2, 4, -1, 2, 0, 1 again, 1, 1/2, and the 4th and the 8th are very difficult to draw. plot there, but they're somewhere down there right next to the x-axis. You want to draw a nice smooth curve through them. That's beautiful. Okay. Should not cross the x-axis, should not touch the x-axis technically. Okay. It should look like that, arrows on both ends. So there's kind of our parent function for exponential decay. How I know that's growth is because the b value, the base, is greater than 1. Here the b value is between 0 and 1. Okay. So that's a decay when it's between 0 and 1. When it's a fraction, it's growth when it's greater than 1. Negatives are not actually part of this family. Like if I put a negative in there like that, that's not actually part of that family. Because if I try to plot that, so every time there's an even exponent, that's a positive value. Like -2 to the second power would be +4. But -2 to the first power is -2. And then -2 to the 0 power would be 1. -2 to the -1 would be -1/2. And then it would keep bouncing like this. And so the graph would do this. And that is a completely different thing than what we're talking about here. So we never do that. And we never put negatives inside the parentheses like that. So our b value would never be negative. We could do this. We could put a negative on the outside like that. That would just graph the graph down instead of up. Right? Just reflect it over the x-axis. You could do that. Mathematically, that is a thing. But it's not something that we really do a lot because exponential functions are really application-based. Talk about population growth or population decrease. When you invest money, okay, money growth or money decrease, okay, radioactive decay. Okay, it's very application-based. We don't have negative money. We don't have negative people. We don't have negative uranium-234. Okay, we can have more of it or we can have less of it, but it's always positive. So mathematically, we could do this. We just don't do it a lot because it doesn't have an application. Okay, so you guys won't really see that. Okay, but it is something, whereas this is not something at all. Okay, so you guys won't really need to worry about that blue thing there, but just let you know. Okay. Oops. The domain for 2 to the x is all reals. We can plug in any number we want. The domain for 1/2 to the x is also all reals. We can plug in any number we want. And that means that nothing's going to make the math go bad. What's the range? Just like 2 to the x, 1/2 to the x is also 0 to infinity. The lowest it will ever get is right above 0. We can never find a number big enough to make that go to 0. 1/2 to the 1/1,000,000th is still more than 0. Okay, and we never have a number big enough to make it go negative either. So always bigger than 0. Increasing interval for the 2 to the x for the growth function. Well, if we look at that from the left to the right, every point is higher than the one before it. Every point is increasing compared to the one before it. So it's increasing over its whole domain. Okay. As we look at the decay function, every point is lower than the one before it. So it's never increasing. Well, that should sure make sense. It's called a decay function for a reason. It doesn't increase. Okay. The decreasing intervals for the growth function. Well, it'd be kind of weird if a growing function decreased, right? As we go from left to right, it always goes up, so it doesn't decrease. As we look at the decay function, as we go from left to right, it's always going down, always going lower, so it's always decreasing. Or what x values cause it to decrease? All x values will cause it to decrease as we go from left to right. The y-intercept crosses at 0, 1. This one will also cross at 0, 1. Because anything to the 0 power is 1. X-intercept, well, we said the range was always going to be above 0, right? So it'll never touch the x-axis. So just kind of some general things for these parent functions. Okay. Of course, they're parent functions, which means they're the most basic of all of them, which means we can do things to manipulate them, like stretch them, shrink them, shift them, reflect them, right? But these are the characteristics of the parent functions. You guys, anything here? Katie? Pepper? Oh, when did you show up? I didn't see you show up. All right. Okay. Let's flip into the next page. So what happens if we start to mess with the function a little bit, right? So f of x equals a times b to the x. Okay, so this is a times b to the x. It's not a to the x b to the x, right? Only the b has the exponent on it. So it might look something like this. It might have like a growth function that's like 5 times 2 to the x. Okay, or we could do like a parenthesis. Okay? We want to make sure that we separate those two things from each other because it's not 10 to the x. Those two don't get to multiply like that. Okay, we can say we want them to multiply, but until we know what x is, we can't do that. So we could also say something like f of x equals 1/3 2 to the x. Okay, so again, I just want to separate the 2 and the 1/3. So this would be a vertically stretched growth function. This would be a vertically compressed growth function. So it's still growth because the b value is more than 1. Okay, but this one would just grow faster than the parent. This one would just grow slower than the parent. Okay, so we can vertically stretch or compress those in the same way we can vertically stretch or compress decay functions as well. I can have, 4 times 1/2 to the x. So that one would decay faster. Well, yeah. Okay, and then this one would decay slower. Okay, so we can vertically compress or vertically stretch these as well, just like we could with everything else. Okay, but what matters is what's the b value. Again, whether it's a growth function or whether it's a decay function. Okay. They're saying increase, decreasing. I'm saying growth and decay. Okay. A has to be a non-zero real number. Okay, so we could do negatives. Most of the time we don't. But it has to be it can't be 0. Okay. It's also the initial value. So if I looked at something like this, the initial value would be 5. Why that happens is because if initial means when time equals 0. Okay. Usually we think about these as time problems, like P of t, the population versus a certain time. So if I thought about that, if this was 5 times 2 to the 0, right? Well, 2 to the 0 is 1, so 5 times 1, that'd be 5. So our point would be 0, 5. So if I had like 5 bacteria, and then they were doubling every hour, I could figure out that. That's what that would represent. Okay, that would be my initial amount. Okay? In the same way, if I had like P of 0 equals 1/4 times 1/2 to the 0, that would just be 1/4 times 1. Right? So that A value just represents our initial amount. What's the problem start off with? If I had $5 and it doubled every year, okay, I can figure out how much I have in 10 years or something like that. But I need to know how much I start off with. Okay, so that's that initial value. Again, B has to be a positive real number. We talked about that earlier. It can't be negatives. Okay, can't equal 1. My growth rate can't be 1. Because 1 doesn't change. 1 to the second is 1. 1 to the third is 1. 1 to the 1,000,000th is still 1. So it has to be something either smaller or bigger than 1. Okay? They're calling it the growth factor all the time. A lot of times, if it's between 0 and 1, I call it a decay factor. Okay, but it is what it is. Okay. Domain, saw that earlier. It's gonna be all reals. We can plug in any number we want. The range should stay above 0 as long as A is positive, which again will be pretty much all we see. The y-intercept, I'm going to change that here. That's going to be 0A. Okay, we saw that here. Depending on what that A value is, that can affect your y-intercept. Okay? On the last page, both of those had an A value of 1. Right? There was just a little 1 right there. There's just a little 1 right there. So that's why our y-intercepts were 1. But now that we start to shift, or not shift, but stretch these, we can change that A value. We can change that y-intercept. Okay. And then the horizontal asymptote should pretty much always be 0. If you had a problem like this, okay, so this would be a growth function that's being shifted to the right 3 and down 4. So we could take that graph and we could shift it. You guys have shifted graphs before. We could do that. Okay, this isn't something you guys have to worry about, but this would have an x-intercept. Where was that? Or sorry, this would have a different y horizontal asymptote. Okay, it would also have an x-intercept, which I said earlier, that doesn't happen. But it's because we're taking that whole graph and we're just dragging it down. Then all of a sudden it would cross the x-axis. Okay? You guys won't be graphing stuff like this. If you're given a problem like this, they'll just ask you to evaluate it and say, hey, what's f of 5 or f of 6 or something like that. That's all you'll be doing. So you don't need to worry about like that messing around with, because that would mess up the horizontal asymptote. It would also change the y-intercept. It would also change the range. You guys don't need to worry about that. All you'll be doing is saying, well, that's 2 to the 6 minus 3 minus 4, which is 2 cubed minus 4, which is 8 minus 4, which of course is 4. So you'd say that 6, 4 would be your point. That's all you guys would be doing with something like this. It's just evaluating it. Okay? But if we had to graph it, it would mess with all this stuff. You guys don't need to worry about that. The range would be -4 and to infinity. The y-intercept would be, whatever you get when you plug in 0, some decimal. And the horizontal asymptote would be -4. Anything here you guys want to talk about? Anything good so far, Colby? You on that?
Yeah.
Okay. A little bit more information before we start doing stuff. So B is a growth factor. Again, they call it a growth factor all the time. I'll say growth factor. I'll say decay factor, depending on if it's increasing or decreasing. So 1 plus R is your growth factor, where R is that percent change as a decimal. So that's important. It's that. So this is a little bit more obvious. If we say there's a 10% growth rate, we would use 0.10 as our R value. Okay, and so then the growth factor would be 1.10. Okay, if we had 100% growth. Okay, so if you had a dollar, then you had 100% growth tomorrow, then tomorrow you'd have $2. Then 100% growth after that, then you'd have $4. Okay, so that means doubling. 100% growth means doubling. That's kind of a weird thing, right? 100% growth actually relates to a 2 because you're taking the 1 you originally had plus 1 more. So that's 100% growth rate would actually be a 2. So that's what that parent function represents, is 100% growth. okay, if you're doubling every time. Okay. If you have a decrease, so this is what I'd call it. I'd call that a decay factor, decay rate. Okay, so if we're decreasing by 5%, right, or 0.05, make sure that you're thinking about that as a decimal, right? It's not 0.5, it's 0.05. This is definitely an area of mistake. Okay. 1 minus that would give us 0.95. So there we're seeing that number that's less than 1. That's why it's a decay problem. Okay, because it's less than 1. A lot of this just is going to come from context of the problem. You're going to read the problem. It's going to say that the population is growing. It's going to say that the population is decreasing, and that'll change how you write this. You don't necessarily need both of these, but because really they're the same formula besides one little thing. But it's all going to come from context. Okay, so here's your final population after, at a certain time. Okay, or your amount at a certain time. This is your initial amount. Talked about that already. Here's your growth rate, and then how much time is passing. Same thing, except for this would be a decay rate, a decrease in population. So you would use a minus instead of a plus. So it's just the difference between these two things. Is it a growth or is it a decrease? Is it growing or is it decreasing? Okay. So if we look at a problem like here, it says the population is growing. Okay, I'm going to add. Look at the next one, it says the population is decreasing. I'm going to subtract. It's all purely context. Okay. These first two examples, there's really no math to do. It's all about reading. Am I reading the problem right? Am I putting the numbers in the right spots? Okay. So A is your initial amount. What are we starting off with? Okay. R is that rate as a decimal. Okay. Definitely, 75%, 0.75. 3%, 0.03. Okay. That's, again, one of the bigger mistakes people make is not putting that other zero there. Okay. If you put just 0.3, that's 30%. A lot different than 3%. And then the T is time. Usually that's in years, but that can change. Okay? If we're talking about, like population of a city, we'd probably want to look over a certain number of years. If we're looking at like population of bacteria, we would not want to look at that over a number of years. We want to look at that over days or minutes or hours or something like that. Okay, so that'll have to be described within the problem. What the time unit is. And here they say, the growth rate is 1.03% annually, right? So there's year word. And so then they were talking about these years. Okay? But if they were saying that the population of bacteria, had a growth rate of 50% per hour, then they would say, well, how much bacteria is there after, 20 hours? Okay? So that time unit can change based off of, what you're talking about. But most of the time, for us, it's years. Okay, whether it's populations of cities or like amount of money you have, or if you're looking at like a radioactive decay, you might be looking at thousands or millions of years. Okay. Basically, we just need to read through the problem and find our A value, our R value, and our T value, and just plug them in. These are formulas. Okay, so there's not a lot of math. It's more about reading. So the population of Canada in 1990, so I'm seeing a year there, was 27.8 million. So there's my initial amount. And how much did I start with? Okay, there's my A value. Population is growing, so there's an important word, growing at a rate of 1.03% annually. Okay, so there's my rate, and they tell me it's growing. And then what's the population in 2018? So I need these years here to help me with the T value. So our A is 27.8. We need to keep in mind that that's in context of 27.8 million. Okay, so when we answer our question, we write that out as millions of people, not just people. Our R value, 0.0103. So make sure we convert that to a decimal correctly. And then our T value, what's the change in time? That's 28 years. Okay, so our T value is 28. But I'm just going to go and plug all that in. I know it's a plus because this is a growing problem. P of t, so our 28 should be there. A, 27.8, 1 plus 0.0103, all to the 28th power. Let's throw that in a calculator. Okay. So make sure you have a good scientific calculator at least with you to do this stuff. 7.8, 1 plus 0.0103 to the 28th power. So they rounded the nearest tenth. So I'm just going to round to the nearest tenth. So I'm going to say 37.0. They aren't giving us a lot of feedback on like how to round. So I'm just going to kind of have to take some clues. So 37.0. And I'm going to use the little squiggly lines there because that's not the exact answer. And because we are rounding, I'm going to use a word like around, about, approximately in my answer. And then that was million people, right? In 2018. So definitely, like, if you're taking a test and you're having to write out your answer, I'd be expecting like a short sentence about your answer, not just an answer. And what's your answer mean? Since it is a word problem, you should have words in your answer. So you're using a word like about, around, approximately, because we did round. Okay. So either of those words would be fine also. So more about reading, more about context clues than actually doing any math. You good, Victoria? You good, Tiger? Next one's pretty easy too. Collapse of auto industry causes the population of Detroit to decrease. Okay, about 2% each year. There's our rate. So 0.02. I should convert that to a decimal correctly. Population of Detroit in 2000 was 950,000. So there's my A value. I'm going to go ahead and just call that 950. I'll just, again, keep in mind that that's going to be in thousands when it spits out. Okay, you can use 950,000. You can use 950. If you change it, you got to make sure you change it back when you're done. And then 2000 was our initial time, so 2020. So our time change here is 20 years. Right? Very straightforward. So pretty much same problem, just this time it's a decreasing problem. So 1 minus. So I'm finding P of 20, 950 times 1 minus 0.02, all to the 20th. Again, you just plug that into the calculator. So not much math, just more about reading. Yeah, they really didn't give me any clues on rounding, so I'm just going to round to the nearest whole number. I'll say 634. And just remember that I chopped off all my thousands earlier, so I'm going to go ahead and put those back on. So 634,000. We're talking about people. This was in 2020. But if you were planning, how many buses you need for the city, if you're planning, working about like you're in charge of the water, you're in charge of blah, blah, you need to know how many people are going to be. So you want to know, be able to predict into the future, like having data, be able to do things like how many people will be here next year? What can we do? Do we need more support services? Do we need less support services? Stuff like that. Be able to predict population growth and or decrease is really important. What cities do. Taxes and all that stuff. If there's less people, then we have less taxes coming in, stuff like that. So the city would need to have a lower budget. Those two problems are pretty straightforward. They're giving us everything. We're just plugging it in, getting an answer out. More about interpreting stuff. The next two, we actually have to figure some stuff out. So I actually have to do some math. Daly doing okay? Maddie, doing okay? So what if we don't know that initial value? Really kind of where this is heading towards is us being able to write the function for this. So the next problem says very specifically write the equation. This one just says, what if we don't know the initial value? I'm going to go ahead and show you how to find the initial value, then also show you how to write the equation from that, which is really generally more what you want to do. This is really what more math is like. We have data, we have information, we need to be able to fit a curve to it so that we can take that curve and then expand on it. Say what's going to happen in the future, what happened in the past. So again, this is really what math is more like. It's not having all the information, being able to find it. So what this is going to come back to is that original function. So P of t equals a times 1 plus r to the t. And I know this is a plus because the values get bigger. The y values get bigger as I go to the right. So from 2 to 3, from 4.5 to 6.5. So that's a growth there. So that's why I know to put a plus. Okay. But when we're done with this, or when we write an equation, what we want to see is that a value. We want to see that r value. Okay. That's what the function looks like. We know what a and r are. T and p of t, we're going to stay variables. That's what the function looks like. That's the thing I plug in. That's the answer I get out. So we need to leave those as letters, but we need to know what these are as values. It's kind of like if I gave you guys 2 points and I said, hey, find the equation of the line that goes between them. We'd want to find the slope between those 2 points and then use that slope in one of those points to then find the y-intercept. And then our m and our b would be numbers, but x and y would stay x and y. So this is pretty similar in that way. We need to use these to help us find one of these, and then once we have one of these, we can then find the other one. Okay? But when we're done, only these two things will be numbers. Okay? So we're pretty lucky here, because if they hadn't done it this particular way, then this problem would be much harder, that these two numbers are sequential. Okay? That there's a change of 1 in there. So if we think of that as if that's what x is, and there's no x in this problem, right? There's t in this problem. That's what x is to us, or t is x, right? So that'd be my t value, that'd be my t value. My change in time is 1. Whether it's 1 day, 1 hour, 1 year, I don't know, it doesn't matter, okay? It's 1 unit of time is changed. So if we go back to the beginning here, I think what happens over a change of 1x. I go from 1x to the next one, right? The sequential one, right? That's going to be a consistent ratio of change, right? 1/8 times 2 was 1/4. 2 times 4 was 8. Sorry, 2 times 2 was 8. 4 times 2 was struggle. 2 times 2 is 4. Right? 4 times 2 is 8. Okay? It's a consistent change. The ratio of change is the same from each gap of 1. When I go from -2 to -1, 4 times 1/2 is 2. When I go from -1 to 0, 2 times 1/2 is 1. That ratio of change is consistent between those gaps of 1. So we can take advantage of that to find the ratio. How do we find that ratio? We take the later one divided by the earlier one. 2 divided by 4 is 1/2. 4 divided by 8 is 1/2. Ratio is the later one, the higher x value, higher t value, divided by the lower t value. So 4 divided by 8 is 1/2. 2 divided by 1 is 2. 1/4 divided by 1/8 is 1/2, is 2. Okay? 8 divided by 4 is 2. Okay? So always take the later one and divide it by the earlier one. That will give you your ratio. Okay? So that's what I'm going to take advantage of here. Again, if they had not given us that, then we couldn't do this easily. There is a way to do it, but again, it's just trickier. Okay? You guys won't need to worry about how to do the more difficult ones. They're going to be above our pay grade. So because that's 1, I'm just going to take them and divide those. And they're going to do that, you get 1.5. So what we just found was this. So we found out what was inside the parentheses. Okay? So that means that our R value is 0.5. So we're looking at like a 50% growth rate here. Again, make sure you always take the later one divided by the earlier one. It's not a size thing. I don't take big divided by little. It's the later one. I know it's later because the time is further along. The later one divided by the earlier one. Okay? That'll give you your rate. Well, now we know this. So I'm going to head back here. We're still looking for A. We're closer, right? We know one more thing. So if I want to know what A is, I would have to know what everything else is. Right? The only way for me to solve for variables is to know everything else besides that. Well, this is a t value, otherwise known as an x, and this is a p of t value, otherwise known as a y. If I had an x and a y value, I can plug those in, and then I can figure out what A is. Well, that's what these are, right? They're x's and y's. Right? They're t's and p of t's. There's a t, there's a p of t. Okay? So I can plug one of those in, one of those sets into here, and I'll be able to spit out A. Okay, but it's got to be consistent. I can't take this x and that y. I have to take this x and that y, or I have to take this x and that y. Okay, Maddie? All right, so the ratio, Maddie, is here. When we do that division, we get that b value, the b value. All right, we get what's raised to the power. Okay, that 4 divided by 2 is 2, and 1 divided by 1/2 is 2. We're figuring out what the base of the exponent is. Okay. Well, what's the base of the exponent here? The base of the exponent is 1 plus r. So if I found out the ratio was 1.5, and that's equal to 1 plus r, I just take the 1 away. I see that the r must just be 0.5.
I'm still confused. That doesn't make sense that you would just take the 1 away.
This is equal to 1 plus r. So if I want to know what r is, I could just subtract 1 from both sides.
Oh, okay. I see. Never mind.
Good question. All right, yeah, so just plug one of these sets of numbers into here and here. Doesn't matter which one you do, just be consistent. So if you're going to use this for P of t, make sure you're using this for t, okay, or the other way around. And we need to solve for a. All right, so let me kind of write down what we did here. The first thing we did was we used the given values to find r. Again, it's almost like finding the slope. That's not slope. It's a ratio. And then we use the r and one of the givens to solve for a. Yeah, so that's kind of the steps we're following here. In order to solve for a, we need to simplify this right-hand side first. We need a single value out of this. So 1 plus 0.5, of course, is 1.5. 1.5 squared is 2.25. So that's the first thing I'm doing. I'm just simplifying this. Okay, so you can just put that in a calculator if you wanted to. Okay, so just doing that math. And then we can see that to get a by itself, we're going to divide by 2.25 on both sides. And then a would just end up being 2. So that is all they specifically said to do. They said, what if we can't find the initial, or what if we don't know the initial value? There's our initial value. But generally what you want to do is write a function from that. And again, in order to write a function, you need to know what a is, and you need to know what r is. We know those two things now. I'm going to go ahead and write the function from that. It'll be more like what we're going to do on number 4. So it'd be like p of t equals 2 times 1 plus 0.5 t. Again, p of t and the t need to stay letters. R and a need to be numbers now. You can also just write it like this. Either way of that's fine. That's generally more what you want to do, is be able to write a function for it rather than just finding a value. That's really about as complicated as that can get. That as far as what we're going to do is if they give you two values, can you find the function that goes between them? Again, I could make it more complex by saying I give you like 2 and then 4.5 and then like 10 and then whatever 10's value is. That's a more complex process, but we're not going to do that. All right, the last thing we're going to get to here. So we want to write an equation for the trout population. So they've stocked a lake with 200 trout. So there's kind of like, it doesn't say that, but there's that initial amount, right? What did the problem start with? They put 200 trout in initially, okay? 3 years later, so there's some time, okay? The trout were at 480. So there's the information we have. We know our A value is 200. We know T is 3. And we have this 480. That's a population. That's an amount of trout. But that's an amount of trout 3 years later. So it's really a point, right? 3 years later, there's 480 trout. Okay? So what don't we know if we're going to write a function? And just kind of look at what the function looks like. What are we missing? Again, what we need to be there is A and R. We don't want T and P of T to be numbers when we're done. We want those to be letters. But you can see that we don't have R. We know what A is. We don't know what R is. Well, if we don't know what one of those is, that means we can plug the A in, and if we have a value for this and we have a value for that, then we can find out R, just like we did here. All right, as soon as we know one of the values, we can just plug in a point, and it'll help us solve for the other value. So since I don't have to find A, since they gave us A, this problem's a lot easier. So I'm just going to take this point, there's my Y value, or sorry, my X value, my T value, and there's my Y value, my P of T value. I'll plug that in there. So it'll look like this. Take that value over there, take this value over there, and we'll just solve for R, the only thing we won't know. Okay, so you can see that R is the only thing we don't know now. So how do we solve that? We should use SADMEP as we're solving. So we look on the outside of the parentheses for any subtraction addition to do. There's no subtraction addition to do on the outside. Look for any division multiplication to get rid of. Oh, there's a 200 that's multiplying, so I'm going to divide by 200. That gives me 2.4 equals 1 plus R cubed. No division multiplication left. Now we're down to exponents. How do we get rid of a cube? By cube rooting. Okay. Most of you guys don't have a cube root button on your calculator. Okay. And we're also going to be doing other roots later. Like if I had to do like a 5th root or a 12th root or something like that, there's no button for that on calculators. So what we're going to do instead is we're going to take 2.4 to the 1/3 power. So as we type that, 2.4 caret 1/3, make sure you put parentheses around that exponent. 2.4 caret 1 divided by 3. Okay, we talked about rational exponents and what they do. And it's been a little while, but that's how they work. Okay, so if you need to take like a 12th root, it'd be 2.4 to the 1 divided by 12. There's a 12th root. Okay? So raise it to that power with that base of the root you want to take. All right, 1 over whatever. 1/5 would be a 1/5 root. Okay? So I got 1.339. I'm just using the thousandths. They didn't give us any idea what place to go to. I'm just using the thousandth. Again, here we see that R is subtracting a 1 just like we talked about. Okay. Oh. Okay. So there we found R, but that's really not what we want to do. We want to write the function. P of t equals 200 all to the t power. Take that a value they gave us, that R value that we just found, and you plug them in. So solving gets a little tricky sometimes because we're really got to make sure you're following SADMEP well.